Today we will discuss about normal modes of longitudinal and transverse oscillation. First we will deal with the longitudinal and transverse oscillation. What are they? Let us consider we have a system and the system consists of a number of particles. If the particle compress at one time and expand at another time, they form a region of compression and rarefaction, and due to this the longitudinal waves or longitudinal oscillations generate. But if the particles in the medium they move to and fro about their mean position in up and down side, then they that wave or the oscillations move in the form of crust and trough, and these oscillations are known as transverse oscillation. If the distance between the particles decreases and increases as compared to their normal distance, then this is your longitudinal oscillation. And in case of transverse oscillation, the normal distance between the particles does not changes. In this longitudinal oscillation, rarefaction and compression regions are formed, due to which the longitudinal waves moves or longitudinal oscillation moves, and the transverse oscillations they move in the form of crust and trough when the particles move in the upward and the downward direction from their mean position. Let us consider the first case, the normal modes in case of longitudinal oscillations. It means the particles are moving like that. Let us consider a system having two particles or two masses, and the two masses are attached with three springs. Let us consider the first mass is our m, and the second mass is also m. Both masses are taken as equivalent masses or same masses, and these two masses are connected with three springs, but the condition is that all the three springs have same length and the spring constant of all the springs are same. If they are displaced from the mean position, let us consider the first mass is displaced with a displacement of psi a, and the second mass is displaced with a displacement of psi b, then we will have the system shifted like that. Again, the spring constant of all the three springs is same, and the displacement of the first mass and the second mass may be equal or may be not equal. In our case, let us consider the displacement of the second mass from the mean position is large as compared to the displacement of the first mass. If we draw the equation for these two systems without any spring, if we have simple pendulum, what will we get in the simple harmonic motion? We will have m psi a double dot is equal to minus k psi a. This is your spring constant, this is the displacement. As we know, F is equal to minus kx. This comes from this relation. And what is m psi a dot? That is mass into acceleration. Again, F is equal to mass into acceleration, and the relation between force and displacement is F is equal to minus kx. And if we combine both these equations of force, we will get this simple harmonic equation. But in our case, the masses are attached with the spring and they have displacement, and we very well know that the displacement of first mass in the direction of acceleration, it will enhance the direction of the first oscillation mass, and psi b, that will decrease the oscillation of the second mass. Hence we have the equation for simple harmonic motion in case of first mass in our case is with a new term, that is k times psi b minus psi a. This terms comes due to the expansion in between the two masses due to the applied force. Similarly, for the second mass, the equation will become minus k psi b. Now, the second term will be negative term because it is in the direction opposite direction of your oscillation. So it will become psi b minus psi a. These are the two simple harmonic motions of two masses which are attached with mass springs and having spring constant k. If both these equations are simple harmonic equations, then the solution of this equation will be psi a is equal to a cos omega t plus phi. That is again the representation of simple harmonic motion displacement. Similarly, the solution for the below equation will be the displacement of the second mass into is equal to the amplitude of the second wave or oscillation. Omega is the angular frequency and phi is the phase difference. At t is equal to 0, the motion doesn't start at the mean position, it starts at a displacement of phi. Now we have to find out the omega angular frequency. In both the cases, it is very easy to solve it. So using equation 1 and equation 2, we can find out the value of psi a double dot, that is acceleration. How will you find out acceleration? Just differentiate it with respect to time. You will get a omega sine omega t plus phi. Again differentiate it with respect to time, you will get acceleration, and now you will have a omega square with negative sign cos omega t. You can calculate it by yourself. You will find out that the acceleration will be cos omega t plus phi. Similarly, psi b will be b cos omega t plus phi. Psi b dot is equal to b omega sine omega t plus phi, and psi b double dot is equal to minus b omega square. We can write it, that is minus b omega square, and this is your cos omega t plus phi. Both these equation can be written in the form of displacement also, as a cos omega t plus phi. Psi can be written as psi a. It means this is our minus omega square and psi a, and this is our minus b psi b. Using these two values of acceleration of first mass and second mass in equation this and this, we will get the ratio of psi a and psi b. Let us substitute the value of psi a double dot in the above equation. You will have minus m omega square psi a is equal to minus k psi a plus k psi b minus psi a. Just simplify it in the terms of psi a and psi b. What will we have? Minus m omega square psi a is equal to minus k psi a plus k psi b minus k psi a. This is the solution for this equation, where we have put the value of psi a double dot and minus k psi a, and we had opened this bracket, and we will have minus m omega square psi a is equal to minus k psi a, and this is so on. This becomes minus 2k times of psi a minus these two terms k psi b and minus m omega square psi a. Just put the equate for psi a and psi b. What will you have if we shift this term in this side? This will become 2k minus m omega square psi a times is equal to, that is equal to k psi b. And for the ratio of psi b and psi a, what will you have? That is 2k minus m omega square divided by k, or we can write in the terms of k by m, that is the normal frequency for simple pendulum. If we divide the whole term by m, you will have 2k by m minus omega square divided by k by m, and this is psi b, that is the displacement of the second pendulum to the displacement of the first pendulum. Let us consider this is your equation number 3. Similarly, we can find out and another relation from these two equations, that is psi b. Differentiate it with respect to time 2 times and put this value in the relation psi b double dot is equal to minus k psi b minus k psi b minus psi a, and just equate for the ratio of psi b and psi a, and we will have psi b upon psi a is equal to k by m. Just calculate it by yourself and you will find out this solution. As equation number 3 and 4 both are representing the ratio of psi b and psi a, we can equate them, and now we can solve them for omega. And if we equate them, we will have 2k by m minus omega square whole square is equal to k square m square. Just take under root both sides, and minus omega square plus 2k by m is equal to plus minus k by m. We have to find out the angular frequencies for our longitudinal mode, and that is we have to calculate omega. In this case, omega have two values. Let us consider first, if this term is positive, that is plus k by m, we will get 2k by m minus omega square is equal to k by m. Just solve for the omega value. If we shift, we will get k by m is equal to omega square, or you can say that omega is equal to under root k by m. It is the simple solution which we get in case of simple pendulum. It means uh, if both the masses are oscillating with this angular frequency, or we put omega is equal to k by m, then from the equation 4, if we put omega is equal to k by m, then we will get k by m, 2k by m minus k by m, and we will have psi b and psi a both are equal. It means they are moving in parallel directions. Both masses are moving in the same direction with the same displacement. They are moving in left direction at same time, and both will move in the opposite direction with the same displacement in the opposite direction. And this is the case when omega is equal to k by m. Another situation, if we take k by m with negative sign, what will we have? This is our equation, and now we are taking k by m negative, it will come this side and this will become 3k by m, and now omega square comes out to be 3k by m. If we substitute this value, omega square is equal to 3k by m, in our equation number 4 or equation number 3, now put this value 2k by m minus 3k by m, you will get minus k by m, and on calculating we will have psi b is equal to minus psi a. This time the masses are moving in opposite direction. It means the masses, if the first mass is moving in the right direction, uh, at this time the second mass is moving in the left direction, they are showing compression. And if the first mass is moving towards the left direction, at this time with the omega square is equal to 3k by m, or we can say that omega is equal to 3k by m under root. This time the mass motion of our system is like that, they are showing the compression and rarefaction regions. It means they are showing the longitudinal oscillations. These are the there are two frequencies. In this case, when they are both moving parallel, the frequency is omega square is equal to k by m, and when they are moving in opposite direction, the frequency is under root 3k by m, which is larger as compared to this frequency. It means when the masses are moving like this, they are moving with large angular velocity as compared to the motion when they are moving parallel to each other, or they are moving in the same direction simultaneously.